Hi, and welcome again to my Physics Online video lecture series. Today's video, I'm going to be talking a little bit about motion on a circle. This is kind of the introduction video within the series that I will do for circular motion, especially uniform circular motion, but circular motion in general, as well as orbits and the like. So today is titled basically like kinematics of motion on a circle. And this is, in some sense, meant to be a complicated lecture, in as much as I'm going to be describing the motion of something around a circle using some sort of 2D kinematics, and it's not necessarily going to make sense from an algebra-based perspective, and I'm not going to go into the calculus-based perspective because that's for maybe a different course or a different audience. The point of this is to show, in some ways, that this is maybe not the best way to describe this motion. So let's say that I have a circle. We'll let it be centered on the origin for the XY axis. The drawing is not going to be great. This represents my circle. All right, so if I have an object that's somewhere on the circle, say right here, this object has an x coordinate and it has a y coordinate. This is something we can hopefully all agree with. I'm going to call this the initial x and the initial y for this object. I'm going to ask, okay, what if it moves to a different spot somewhere else on the circle? So after moving for some time, now it has a new value for y and a new value for x. And I can determine on here both the x and the y displacement. For example, delta x should look like x final minus x initial. We can even describe those as vectors. And delta y should look like y final minus y initial. Again, we can describe that as a set of vectors. Okay. Now, so far, this should be fairly straightforward. We can see what x is doing, we can see what y is doing, and now maybe we want to know what was the average velocity for this interval where it started here and ended here. Well, okay, we know that delta v, the velocity, should be defined as basically like rate change of displacement. So this would be delta of, I'm going to use a little s for displacement over delta t, where s is given by the x vector plus the y vector. Now, in algebra-based physics, we don't have a very good language for x and y vectors. Again, you could think of it as being like, where do I draw the dash line down to the x-axis, and where do I draw the dash line over to the y-axis? And these two things can't just be added together as x plus y. You have to add them as vectors. So there's an x component, there's a y component. I have a change, then this is suggesting that I have a change in the x component and a change in the y component. And I wrote a delta. This is not a delta, it's just a velocity. It is actually an average velocity. Okay, so if we say all that, then what does that mean? Well, basically, in order to figure out what this velocity is using these two-dimensional points, I would have to be able to essentially draw a displacement from one point to the other like this, and this would represent my delta s. All right, so I'd have this vector and I'd divide by the amount of time that that's taken, and that gets me my average velocity vector. So that should be reasonably straightforward. But now we throw in a further complication. What if instead of getting average velocity, I want to get the average speed? Well, we can see immediately that that's not going to give me the same magnitude as the magnitude of the velocity vector, because this right here would represent my actual distance traveled delta s, and therefore my actual average speed, which should look like the distance traveled divided by the time, is not going to be the same as the magnitude, or in other words, equivalent length of this vector divided by the time. In other words, this red curve is longer than this yellow line that I've drawn. So we can't just do that anymore as we have with much of our 1D kinematics. We can't even do it as easily as with 1D kinematics where we broke it up into pieces and add up each of the pieces. It is, in other words, a two-dimensional motion that we're dealing with here, which is to be expected. We're moving on a two-dimensional surface. Okay. So we can get velocities, and those velocities, they work out in some way. It's not too big of a deal to measure these distances. But now we get to the next component, which is what about acceleration? So remember that acceleration is rate change of velocity. So A should look like delta V over delta T. And that means that we now have to figure out at what rate is this velocity changing. And that includes a direction and it includes a magnitude. So among other things, it should be evident that the velocity changes even if the speed remains constant. And if that's not immediately obvious to you, let me do the following. Let's draw another point right here. So this might be like a later time, sometime after what we called our original final time. And this object now has a new displacement. This is like delta S2 from where it started to where it ended. And so this displacement and this displacement very clearly are not the same. They don't have the same direction. That also means that the velocity must have changed direction in here. And that means that even if this is moving at a constant speed, I have non-zero acceleration, which I have to somehow be able to extract from all this. Now, again, taking this as a physics that is based in algebra kind of approach, you should be looking at this and saying, this looks more complicated than what we've been doing in physics. Even if what you've been doing seems complicated to this point, I think that this should seem to you to be a little bit more complicated. And again, remember that the point is I'm showing you a complicated way because I want you to then see when I do this again, a simpler way, that the simpler way really is simpler. Case in point here, we've said that this acceleration is not constant, even if the speed is constant. The acceleration is non-zero. It's not even a constant acceleration. The direction actually changes. I will state here without proof that for each of these dots on this circle, assuming a constant speed, the acceleration will look like this. So each of these dots gets an acceleration, and each of the accelerations for a constant speed will have the same magnitude, but you'll notice that the direction has changed for each one of these. Okay, so the acceleration is non-constant here. And in an algebra-based course, we don't even know how to deal with, at this point, a non-constant acceleration. We don't know how to deal with that, what the motion should look like or anything. So in some sense, we've kind of like hit the wall. We can figure out that there is an acceleration. We can maybe figure out how much force is needed to produce that acceleration, but we have no way of extracting from that acceleration what the kinematics should look like without resorting to something beyond algebra. We could maybe do some interesting geometric proof, but it will be longer than what I have for this video. It turns out that the x and y components can be, in some sense, reduced to a different coordinate system and expressed in terms of a different set of coordinates. And if we do that, then life gets a little bit easier. For example, it turns out that our x component of velocity should look like some value, which I'm not going to explain here, times r, negative of that value, times r, times the sine of that same value times time. Okay, assuming, of course, a constant speed. So this is constant speed. And the x component of acceleration, as it turns out, ends up looking like negative omega squared times r times the cosine of omega t. And I should note, how am I defining r? R is actually just the radius of the circle. Okay, so that one's obvious. These two are not. And I'm going to leave them as kind of a mystery for this video. Similarly, I can write out Vy and Ay. And I've got vector symbols over everything. That works with a plus and with a minus. Minus being left, or plus being right, minus being down, plus being up for the y. So Vy will look like omega r cosine omega t, and Ay will look like negative omega squared r sine omega t. So this looks like a fairly complex set of parameters. And in actually a later video that's not really in this section but is related to this section, we'll see that these are what we would call oscillatory equations. In other words, if we plotted them, they kind of make a motion that's up and down like a sine or cosine. In fact, you should be able to predict that by the fact that they have the equation sine or cosine, cosine or sine in. So you know that they're sinusoidal. This means that they're also oscillatory. So this makes for a very complicated picture of where is stuff at a given time. And by the way, where is the actual object at some given time? Well, you have to have x is equal to x initial plus delta x. And good luck getting delta x from algebra using these two equations. That delta x actually ends up, as it turns out, being r times cosine omega t. And for y, I end up getting y initial is y is represented by y initial plus r sine omega t. All right, that's all I'm going to do in this video. There's only one slide of notes. The explanation took more time than the writing this time around. Normally, I would say here, I hope you learned something, and I do kind of hope you learned something from this. Normally, I wouldn't say, I hope you leave this video feeling confused, but for the method I'm using here, I do kind of hope you leave this particular video with more questions than you started, feeling kind of confused about how you're going to be describing this motion, because hopefully that'll make it make more sense why we would want to switch coordinate systems and use a different system to describe this motion. So that's all for today's video. Thanks for watching.